Good evening to all. This is Kashyap Vasudevan, one of the TAs for the course Foundation Engineering of NPTEL, which is the course instructor is Professor Kousik Deb from IIT Kharagpur. This is the interactive session for week 6. So we are halfway through since it is a 12-week course. So, okay, so we'll be discussing about the contents which was of week 6 and so as usual, let us begin with a recap. Um, so uh, we began week 6 with discussing about the problems of design of shallow footing and uh, different methods we have in our hands, which is the primary one was Terzegi's method, and which is very simplistic and very fast. We can do it very easily. And we have Meyerhof, Hansens, and Wessex, which are quite similar, and only the differences are between uh, while calculating the shape factors, depth factors, and inclination factors. Other than that, we have IS code method, which is very similar to Meyerhoff's method, and again there is a slight difference between the in the formulas. After this, after solving a few problems, we in this week 6 we entered to pile foundation. Pile foundation is one of the deep foundations. That's when we use, like when we have when though we generally consider shallow foundation first. There are many conditions where it may not be sufficient, because either the load will be very high and our bearing capacity available at the shallow depths will not be enough, and so we'll have to go deeper and deeper while doing soil investigation and find a competent layer where we can expect a better strength. In such cases, rather than shallow foundation, we'll have to go for deep foundation. The most popular deep foundation that we adopt nowadays is pile foundation. Okay, so what happens is, like, we bore a hole and we install a pile, generally made of concrete. If you're, there are other materials also, and it reaches the competent layer such that the resistance offered by the cylindrical or it depends in shape of this long member is enough to resist our load. Okay, so this you must have you must have seen this in many different structures, like high-rise buildings, bridges, even a few story building, like 3 to 4 story building. Also, if it is if the competent layer is not if the shallow layers are not strong enough, we will have to go for deeper deeper foundation. And pile foundation you must have also found in harbors and many different structures. Okay, so as we told before, there are different uses of piles. Pile foundation, generally, like, the foremost use is like to resist the load. So when we say load, it can be vertical, and even when we say vertical, it can be two different loads. It can be compressive load or tensile load. So generally, very common one is compressive load. So the load will be coming from the top, from the superstructure, and the the pile will be resisting it in two different ways. They're like either by bearing at the bottom, it will resist by bearing, and also with its surface, which is a vertical surface around it. The friction between the soil as well as the pile material surface, that will provide also a resistance. So depending on that, we can call it end bearing pile or skin resisting pile. Okay, so when we say vertical, it can be either compressive or it can be tensile also. When I say tensile, it is generally found in tension piles, and that the condition is like, especially when there is a high-rise building, or even when there is a wind, a structure which is susceptible for wind resistance. For example, electrical tower or lightweight structures which are which goes very tall. In such scenarios, the wind load becomes quite significant when compared to its mass, and that can cause uplift. We have a the base of the structure, and if there is a wind load acting like this, there's a chance of uplift in this area. So that uplift pressure has to be resisted. So those piles which resist this uplift are called tension piles. And so that is also a way. So, and when I say load, it can be horizontal also, or inclined also. Inclined is nothing but we can resolve it into horizontal. So horizontal loads, in that we can get laterally loaded pile. Laterally loaded pile are generally found in harbors, or even some retaining walls we can use. Okay, another use of pile is to there are certain kinds of piles which are just uh, installed for compaction. So we will not be discussing that here because we are concerned about load bearing piles. So what happens is, while installing the compaction piles, the soil which is in loose condition gets stiffened because of this installation, because the surrounding soil gets laterally displaced, and that's how it is. And after that, we moved on to types of piles. Types of piles can be on the basis of many different scenarios. For example, material, we talked about it can be concrete, wooden, or steel, or it can be composite also, made of two different materials or two or three different materials. Cross section, the shape of the cross section can be different. We generally deal with circular or square, or even sometimes hexagonal, uh, or sometimes I section, H section. There are multiple different section, cross section shapes available. Depending on application, we can choose. Shape of the pile can be generally cylindrical or prismatic. We go for. Otherwise, it can be tapered. Tapered in the sense, the top of the top dimensions of the cross section area of the pile will be higher, and at the bottom, as we move to the bottom, it will gradually, in a linear basis, it will reduce. So this can also be used, tapered piles, and other shapes are beveled piles. So when we have under reamed piles, so under reamed piles are like we have a bulb at the end, and so it's generally used for uplift pressures. Another basis is mode of load transfer. As I told you before, the load can be vertical or horizontal. So even in vertical, there can be tensile or compressive. So when I say compressive and tension, when I explained it, generally there are two mechanisms, as I told. One is from the bearing at the bottom. So since it has a cross section at the bottom, it will resist from bearing. And another thing is by the screen friction, the surface between the pile material as well as the soil. So though depending on that, we can say whether it is end bearing pile or shear piles. Then method of installation. By method of installation, we mean to say the way it is installed in the field. For example, it can be either driven, that is, the pile is ready and we are applying impulses so that the pile is driven into the soil, or it can be bored pile. So what does that mean is, like, we can bore a hole, and we can either drive on it, or we can even immerse, no, not immerse, we can set the our wire mesh, our reinforcement mesh inside the borehole, and we can pump in the concrete using different machines. So these two different piles have different advantages and disadvantages, which was clearly discussed. And method of forming, we can form the concrete pile in two different ways. It can be precast, so or it can be pre-stressed concrete, or it can be normal concrete. So depending on that, the method of forming also we can classify using that. Displacement of the soil. So there are two different ways. Either we can displace the soil because of our driving, or the soil may not be displaced in case of boring. So it's generally it goes parallel, but there are different conditions in which because here the concern is soil, whether it is moving laterally or not. Because moving, if the soil is moving laterally, then we can expect more compacted soil around the pipe. After that, we came to calculation of load bearing capacity of a pile. we discussed different material. We just started calculating the load bearing capacity, and even in week 7, we'll be proceeding with that. Okay, so having said that, let us move on to the first question. So there are two questions which are quite long in this. So bear with me. Okay. The first question is like, as I told, we were discussing about footing itself. So in shallow footing, here we have a question about using Mayer-House method, how to find the net ultimate net bearing capacity. So we in the last class we had discussed about IS code method as well as Terzaghi's method. So here we will do Mayer-House method. Though this question is just about Mayer-House method, we will also extend it to Hansen and Vesic just to compare how it goes. Okay. So having said that, here it's in this particular case, it's quite convenient because we have shape factors given directly, but we will find it for the Hansen and Basics later. Okay. So we are given a C5 soil. C and 5 values are given. We know the densities of water and this thing. 2.2 meter is the depth of the footing, and it's concentric. So if you had attended the previous interactive session, we had discussed about eccentric loaded footing, as well as in the tutorial, sorry, in the videos also we also discussed about this thing, inclined load. So in all those cases these factors differ. Okay. Now basically we are also given this our bearing capacity factors, three bearing capacity factors for our 5 value. Okay. Now, assuming that it's a general shear failure, let us move on using Mayer-House method. So, since we have this, let us just write it down. We have a ground level and footing, and the depth of the footing is 2.2 meter. Water table is given as 1 meter below the footing. So, this is water table. Sorry, this is 1 meter below the footing. So, from this level, this distance is 1 meter. Okay. So having said that, we have the density also given as 19.7 kilonewton per meter cube. Okay. So since we are talking about bearing capacity, we are interested about this particular distance, that is be equal to the width of the footing, that is 3 meters. So we have 3 into 4 meter footing. Okay. So because in our third term of our bearing capacity equation, in order to find the density, we need this depth. So we are supposed to take weighted density at this of this layer. Okay. So to begin with, what is this density? So let us make it very clear. This pressure from top, we can calculate now itself. That is um, at at foundation level. At foundation level, our density, our pressure is 19.7 into 2.2. That will be 43.34. And we are also interested to get the average weighted average density of this particular layer of this 3 meter below this footing. That is for the third one. This is for the second term. That is if I write Q and U is equal to C and C uh, plus Q and Q with the other factors also. Okay, I'll write it properly. C and C, SC, DC, IC plus Q and Q, SQ, SQ, DQ, IQ plus half gamma b n gamma s gamma d gamma I gamma. This is the general equation for all the three cases, Meyerhof, Hansen, or basic. But here we are getting ultimate, so we have to subtract it by our uh, overburden till the footing level. So this I can also write as q. So the second term q, that is this particular. So in the third term, we also need a density. That density will be weighted average of this B level. So in this B level, we have water table. So we'll above the water table we can take 19. So I can write it as average of this. I can write it as 1 into 19.7 plus 2, that is the rest of the depth is 2. So 2 into 19.7 minus 10, that is a submerged weight, unit weight, divided by 3. So the average weight of this gamma is 13.03 kilonewton per meter cube. Okay, so having said that, let us solve the thing. So we have the all the bearing capacity, sorry, not bearing capacity, shape factors and depth factors. We need not want inclination factors because inclination is not mentioned, so it's axial loading. It is mentioned that it's axial loading, so inclination factors doesn't matter, we can take as one. And eccentricity is also not there. Okay, so let us just write our the values. Nc is equal to 30.1, NQ is equal to 18.4, N gamma is equal to 16.7. Likewise, shape factors, SC is equal to 1.45, SQ is equal to, S gamma is equal to 1.225, and depth factors, DC is equal to 1.245, DQ is equal to, D gamma is equal to 1.127. Okay, so we have all the factors. Let us just substitute and see what happens. Q and U is equal to, first C and C. C is equal to 15, NC is equal to 30.1, SC, DC, IC. SC is 1.45, DC is 1.245, IC we can take it as 1, plus uh, next is Q and Q. Q was 43.34, into NQ is 18.4, SQ, IQ. SQ is 1.225 plus, sorry, not plus, into DQ is 1.127 into 1. IQ is 1. So the third term is half gamma B and gamma. So half gamma dash. So our weighted average we have to take, that is 13.03. B is 3 meter. N gamma is 16.7, and S gamma, D gamma, I gamma. S gamma is 1.225, D gamma is 1.127, I gamma is 1. This is our ultimate, so we have to subtract it by our gamma df. So gamma df can be written as 19.7 into 2.2. This turns out to be 2323.3 kilometers. And I guess one of the options are very near. Yeah, this must be the nearest. This must be the answer. Okay. So Meyerhof we have done. The only okay, so we can move on to Hansen's method, but the only difference is actually when you compare Meyerhof's, Hansen's, and Wessig's, the only difference are in the shape factors and depth factors. The formulas for that, and N gamma values are also a little different. Rest everything, the procedure and all, everything will be the same. So let's move on. So for Hansen, I would really suggest you to look at this table because this is available in Bowles textbook. Joseph Bowles, 1996. So in this textbook, he has given summarized every factors formulas in this 4.5 table. The 4.5 table, if you go through A, B, C, there are three tables. We'll come to that. We can get different factors. Okay. So when we are doing Hansen's method, now let us do Hansen's method. The only difference is okay. So before I say one major difference is n gamma. In NC and NQ will be the same. So n gamma, if you see, the formula is given as, let me just verify. Okay, in Hansen's the formula is given as 1.5 into NQ minus 1 tan phi. So if I substitute, I'll get 1.5 into our old NQ. 18.4 minus 1 into tan 30. How much does this come? Let me just verify. 1.5 into 18, that is 17.4 into tan. Okay, so this comes out to be 15. Now, okay, just like that. Now, after, so the other things are shape factors and depth factor. Shape factor is given as S C is equal to 1 plus NQ by NC B by L dash, B dash by L dash. Now NQ is the same as Mayer house, that is 18.4 divided by 30.1 into our B dash and L dash is 3 by 4. Here B dash L dash, because if we had eccentric load, we, as if you remember properly, if we have eccentric load, we have to reduce the dimensions of the footing. So that reduced dimension of the footing is B dash and L dash. That is nothing but 2 times the B dash is equal to B minus 2 times eccentricity, and L dash is equal to L minus 2 times eccentricity along y-axis. So that thing is already discussed before. So that is the significance of this B dash and L dash. Since here we are not concerned about it, we can directly substitute B by L. Okay. So that is actually one of the difference between Wessex and Hansen's. Wessex we use B dash L dash, but Hansen's we, okay, the other way. Hansen we use B dash and L dash. Wessex, in the Wessex factors we only use B and L, irrespective of whether we have eccentricity or not. Okay. Now other factors, SQ is given as 1 plus B dash by L dash sine phi, that will be 1 plus sine 30 into 3 by 4. This is 1.375. Okay, I didn't write the value. This is 1.458, and S gamma is equal to 1 minus 0.4 B dash by L dash. This should be greater than 0.6. If it is less than 0.6, we have to take 0.6. So this turns out to be 0.4 into 3 by 4. This is 0.7. Okay, so we have all the values of shape factors. Now let us find the depth factors. So depth factor DC is given as 1 plus 0.4 K. What is K? K is nothing but D by B. If this is only if D by B is less than or equal to 1. If it is greater than or equal to 1, sorry, if it is greater than 1, if it is greater than 1, we have to take tan inverse of K is equal to tan inverse of D by B. Okay. So K here, what we have is K is equal to 2.2 by 3, right? That is 0.733. So we can substitute here 1 plus 0.4 into 0.733. This is nothing but 1.2932. Next is dq is equal to 1 plus 2 tan phi 1 minus sin phi. This little complicated, this particular equation, but we need not memorize it. Generally this will be given, but the uh, for basics also this holds good. So uh, 1 plus 2 tan 30 1 minus sin 30 square and 0.733. This value is 1.2. Okay, so dc we have, dq we have, next is d gamma. D gamma is given as 1 for all 5 values. Okay, now it's I as I told you, it's everything is equal to 1. So let us directly substitute. QNU is equal to CNC, so 15 into 13 point, sorry, 30.1 into 1.458 into 1.2932 into 1 plus 43.31. This is our Q into NQ 18.4 into 1.375 into 1.212 plus half into 13.03. This is our gamma dash into 3, that is B, zero point 0.7 into 1 into 1 into, okay, I forgot n gamma, right? So n gamma is 15.1 into 0 0.7 into 1 into 1 into 1. Okay, only 1. Okay, so 3 terms are done and we have to subtract it by gamma df. So that is 2.2 into 19.7. So what we are left out is with 2344.185. Okay, kilopascal. That is basic. Sorry, Hansen's. The in basic the only difference is as I told you, that is b dash l dash. In basic, whether we have eccentricity or not, we will use only b and l. And the another only change is this, instead of this sign we had here, it will be tan. So just sc will be same in basics. Sc will be same we had before 1.58. Sq will be 1 plus b by l sine phi. Last time we had tan phi. In Hansen's we will have sine phi. So this is 1 plus 3 by 4 tan 30. Sorry. Okay, this is sine. In basics we have tan phi. So tan 30. This turns out to be 1.433. And as usual, this is same as Hansen. So this is 0.7. So having said that, and depth factor, everything will be same. So dc is equal to the same thing that we had before, right? Dc is equal to, okay, not, this was k value, right? Dc is equal to 1.297, dq is equal to 1.212, and d gamma is equal to 1. Okay, so this is same as Hansen. Okay, so if you look at it, there is only one particular thing given, that is common for both. Okay, so let us just substitute and see. QNU is equal to uh, okay, QNU is equal to the same thing. Okay, wait, I think I made a mistake here. DC value 1.293. Okay. So 1.2932. Okay, sorry. Let me start with C and C. C is 15 into the 30.1 into 1.2932 into SC is 1.458 into I is 1 plus uh, Q and Q. Q is 43.34 into NQ was NQ is 18.4 into 1.433. SQ has changed, so we have to write that into 1.212 into 1 plus half into gamma into B into N gamma. Gamma B and gamma is 22.1. Okay, I forgot to say that in V6 we have in V6 N gamma equation is different. As I told before, this was for Hansen. This particular equation. For V6 equation, it is different. We have N gamma is equal to 2 into NQ plus 1 tan phi. So this turns out to be 2 into 18.4 into, sorry, 18.4 plus 1 into tan 30. This is 22.4. Okay. So here N gamma is 22.4 into zero point 0.7 into 0.1 into 0.1. And we have to subtract it by gamma d. So that is into 19.7. So whatever you left it, QNU is equal to 2500.6. Okay. So we have done basics, Hansen's and Meyerhoff. It seems like Meyerhoff's is 2332, slightly, almost everything is same. Meyerhoff's is the least, then comes Hansen's, then highest is basics. But this pattern we cannot expect in all cases. It depends on the soil property and the size of the footing and all. So we cannot generalize it, but it will be different. So there are we need to understand a few things. Okay, before that, the one of the things is like Terzaghi's is the easiest one. So Terzaghi's is better to be. So when to use which method? That is a big question, right? So Terzaghi's is simple, but it doesn't take care of many things, right? So in the beginning, if you remember, it didn't take care of the shape of the things and the depth of the footing and all. So it's very simple and it's fast. So if you want though it is no, it's not considering many things, it will give you a fairly good enough value of bearing capacity. So it's simple and fast. So when you want those things, you can go for Terzaghi's. But basics, okay. Meyerhoff, Hansen, and basics are it can be generally used for in almost all cases, almost all scenarios. We can use it. Uh, but these two are a little special because this also considers here the advantage is it considers shape, depth, and inclination. But if you want in Hansen and Wessex, it also considers base inclination as well as ground inclination. So if our footing is a little the base of the footing is a little inclined, we can they take care of that. And also if the ground of the ground above the footing is a little inclined, that also we have different factors. So our factors will be like SC, DC, IC plus PC, GC. So if we have all these scenarios, we can we can take account of that. Just like that, the second term will be SQ, DQ, IQ, BQ, GQ. So that also can be taken into account using Hansen and Wessels. We have one more thing that we have is IS code, but we know IS code is the method adopted because of the legal issues, and that is very similar to our Meyerhoff's method. Okay, so having said that, we can move on. So as I told you before, the ground factors. So we have ground factor as well as base factors. Ground factors are used for slopes when the ground level is a little inclined. Base factors are when the base of the footing is tilted. So for both Hansen and Vesic, we have these factors. So I would recommend you to go through 4.5 table just to have an idea where to look at uh, and how to uh, do this. So inclination factors is already used. This is a very rare case where we have base factors and ground factors. So this is just for your information. I guess we can move to the next question. So now we have entered pile foundation. So pile foundation. This particular question is just to find our ultimate capacity. So we have two components, if you remember. One is from the bearing capacity, that is the base of the pile which is resting on the soil, so that provides some resistance. Another one is with the skin, in and around, around the pile, which the soil is providing another resistance through the skin of the pile. That is due to the skin resistance. So these two can be added to get the ultimate pile capacity. So we are given certain values, but the units are different, inches and feet. We can convert that, and we'll come up with the so first part doesn't have any water table, second part will use water table. So here there is a concept called critical depth concept. This concept is actually discussed in the next week. So this week we need not enter that, but we will towards the end of the session we will come to that. Okay. So we are supposed to use Tomlinson Beresensev's method. Okay. So okay. So let us dive into this. Here we are also said that it's a concrete pipe. That is also relevant in future. Okay, we will see that. So let's first get into this. So we have basically QU. This is the ultimate capacity. So as I told you, we can split it into bearing as well as shear. That is the skin friction. So this is nothing but Q into QUP into AB plus QS into AS. So this is the bearing resistance. This is a bearing resistance. This is the skin resistance. Now, since bearing resistance we can find out, we are quite familiar with it. It is very similar to our bearing capacity of the footing. Because at the base of the footing, whether it is circular or square, we can idealize it as a just like a footing, and there must be some bearing capacity at that particular depth, so we can arrive at this particular uh, this thing. So since that is a case, AB will be our tip area. So area of the base of the pipe, and AS, so skin friction is acting on the surface. So the if it is a cylindrical pile, we have the curved surface. So that is a surface which is on which the skin friction is acting. So this is the shearing area, can I say? If I say shearing area, I hope you can understand. So if at all if this is my pile, uh, so this particular area is what I'm talking about for in the case of bearing, and the case of shearing, the curved surface. So at the bottom this part is not taken and the top also not taken. The curved surfaces are shearing it. So this is the basic thing. So area we don't have any issue. The issue will be with the bearing resistance and skin resistance. How are we going to calculate it? So in whichever method we are going to study, the basic problem is with this bearing resistance and skin resistance. So the different people will be coming up with different methods. So in our case, for Tomlinson's method, we have uh, sigma nq. Okay, sigma nq ab plus, this can be written as sigma average k tan delta as. So AB and AS we are not worried about. It depends on the cross section area, how the dimensions of the pile. But this is the thing that we are concerned about. So Tomlinson provides this particular equation. Okay, so this is QUP, the whole thing, and this is QS. Okay, so let's begin. Um, First, talking about bearing. Okay, so here, what are the sigma values? These sigma values are, if we can crack, if we can find out these sigma values, our job will be very easy. Because this sigma we are dealing with our the base. So what is the vertical pressure at the base of the pile? So this particular pressure we have to take it here, but this is the average pressure. So if we are idealizing the vertical pressure as in a triangular form, the average will be the this particular, sorry, so it will be half of the base. So if you are trying to take an average of the triangle, so if you are yeah, taking as equivalent rectangle, the side will be half. So because that is the average stress happening in this curved surface. So here this K value is nothing but to make it as a lateral pressure. So effectively what we are doing is we are trying to find the lateral stress, lateral pressure acting on the pile surface, because tan delta deals with the friction. So this will be the normal stress, and multiplying by friction we can get the shearing resistance at the tip. So this sigma average is nothing but our average vertical stress from our starting of the pile to the end of the plane. Okay. Okay, so let's start. In the question we have a pile which is 15 feet, sorry, 50 feet, right? 50 feet comes out to be 15.24 meter, and we have dimension as 16 inches into 16 inches. This is nothing but zero point 0.4 into 0.4. So from the dimension we know that the square pile. So the it would look like this from top, 0.4 meter into 0.4 meter. Okay, so gamma is given as 110 pounds per feet cube. Okay, 110 pounds per feet cube. That can be converted as 70.28 kilonewton per meter cube. Phi is 30. Okay. So in Tomlinson's method, we need to find this NQ. So NQ, whatever he says is, there is a chart given. In the chart, we can arrive. So this is a chart given for Tomlinson's method. So this chart we have internal angle of internal friction in the x-axis, and bearing capacity factor in the y-axis. So our particular angle is 30 degree. So let us see. We need L by D. So what is L by D? L by D ratio for our case, its length is 15.24 divided by depth. D is nothing but diameter, or since it is square, we can take it as 0.4. This turns out to be 38. uh, and so okay, so let us see this table here. 38, okay, angle is here, so 38, this particular last curve is 70 and this is 50, 20, so 38 will be somewhere in between. So if we just try to draw a line from here, I think I can write it as 20. So it depends on your judgment. uh, if you can try to get your own, like it might be here and there, but let me take it as 20. So our NQ value is 20. What else do we need? We need sigma dash, right? So sigma, our q, sorry, so at the base. So here let us hypothesize that this particular is in a triangle fashion. So just there is a conventional way we can say this is nothing but gamma h, right? So that will be 17.28 into 15.24. That will be 263.34 kPa. So this is the stress at the pressure at the base of the pile. So this we need for bearing capacity term. So what is the average? Average will be since here it is 0, 0 plus 263.34 divided by 2. Okay, we'll come to that. So let us see. Here we have, let me write the first term. So if I'm writing Q is equal to QUP plus Q S. So QUP I can write it as sigma NQ into AB. So sigma is 263.34 into NQ, we got it as 20. 20 is NQ, 20 will be very less. So since our phi value is 30 degree, we are getting a very low NQ. So suppose we get a stronger soil 35, NQ drastically increases. So that will drastically increase our bearing capacity. So NQ is 20. A of the bearing will be, since the square, our area is nothing but 0.4 into 0.4, right? So this turns out to be 842.6. We get this in kilonewton because this particular term is in is nothing but QUP, right? So that is kPa, kilometer per meter square, and here we have meter square. So our answer will be in kilometer. Okay, so after that, let us go to the shearing part. So for shearing, our equation was to get QS, we have sigma average into K tan delta, right? So here sigma average we know sigma average as half into 260. Okay, we'll start from the top. 0 plus 263.34. So we have taken the average stress into K. So this is given by Brahms. So Brahms, what he did was he gave the values for loose sand and dense sand as well as the delta values. So here we are dealing with concrete. So this is the column. So first we have to decide whether our sand is loose sand or dense sand. So in this table, this is also given in bowls. So our particular angle is 30 degree, which comes under loose. So taking it as loose, even you can take it as medium, but worst case scenario, let us take it as loose. So loose sand, this column we have to take care. So this is concrete, so our K value will be 1. So K value is 1 and delta is equal to 0.755. So 0.755 is our 30 degree. This comes out to be 22.5. So I can write it as tan 22.5. So the whole thing will be 48.95. So our QS is nothing but this small QS into AS, right? So AS is nothing but the surface which is providing the shear skin resistance. So that is nothing but the vertical surface, that is nothing but the perimeter into length, right? So perimeter is 4 into 48.95, 4 into side for square, so 0.4 into length. What is the length? 15.24. This turns out to be 11393.59. So we got QS. Now if we just add the both, QU is equal to QUP plus QS. This will be 206. Sorry, 236.27 28, let us say. Okay. Okay. Now this is the estimate. This is our pile capacity, 2036 kilonewton. So what will be the safe pile capacity? Q safe will be equal to, if we are taking 2.5 as the safety factor, Q safe is equal to 2036.28 divided by 2.5. 2.5. This will be equal to 814.51. Okay. So there is one more issue here. The small thing. This is when we are trying to attain exact capacity, because also the weight of the pile is also contributing to the load. So if in our load calculation, if we are not calculating that, we need to write Q ultimate as Q PU plus QS minus W, right? W is nothing but the weight. So if I find weight is equal to, I can write 0.4 into 0.4, that is the area into length of the pile. So we got the volume of the pile into 24, assuming that 24 kilonewton per meter cube is the density of the concrete. Having said that, we can get this as what is this weight? 58.52 kilonewton. But compared to this, it's very less. So if you want a rough estimate, we need not consider it, but just for an exact value, we can write safe is equal to our net ultimate. This is nothing but 200, right? 2036, right? So 2036.277 minus W is 58.52 divided by 2.5. This turns out to be 791. So 791. So our last figure was 814.51. Now it is 791. So it has just slightly decreased. But in our strict design, we will have to consider that. Okay. So we'll try to extend the question to a little further. What will happen if we have a water table at 5 meter below? So let us say that we have a water table which is 5 meter below the ground surface, and let us say we have a, this was nothing but 19.7, right? 19.7. Sorry, this was not 19.7, this was 17.28. 17.28, 19.7, that was in the previous question. And let us assume that this sat is equal to let us say 19 kilonewton per meter. So if we have water table, what will happen? We know that by intuition we know, since we have added water table, the capacity will decrease. So let us just see how it decreases. We have a pressure, right? So till here water won't be there, so effective pressure we are trying to get, so it will reduce, it won't be the linear line, so it will reduce. So this particular thing will be uh, 17.28 into 5, that will be 86.4, and this particular thing will be the same thing, 86.4 plus our effective overburden pressure due to this layer, so that is uh, 19 minus 9.81, that is our submerged unit weight, into uh, 10.24, that is this distance is 10.24, because I have subtracted this 5 meter. Okay, so this value it turns out to be, I hope you can see, this value turns out to be 180.51. So we are starting with 0. At the water table level we have 86.4 kPa. At the base we have 180.51. So 180.51, why is it required? We require it for that first term, that this bearing term, and we require the whole this distribution, how the vertical distribution is for our shearing resistance, right? So having said that, let us first find this QU for the part 2. So this will be part 1. So in part 2, QUB is equal to, so let us just find the first, sorry, not UB. Let us just find the stress. QUP is equal to gamma dash NQ. What is gamma dash at base? That is 180.51. That is 180.51 into our NQ remains the same, because phi value we are taking it as same as 30 degree. And L by D is also same. So NQ will be, so our QUP will be 3610.1 kPa. So our capital QUP will be 3610.1 into, what is our area at the base? That is zero point 0.4 into 0 0.4. So this is 5.77, 577.6 kPa. Okay, so we have QUP. Our issue will be with shear, because what is happening is, I can take it as a whole average, but it will be better, if we'll get a better answer, correct answer, if we are taking it as two separate layers. So the thing with shear resistance is, we can divide the pile into two phases. So this resistance as well as this resistance can be separated, because the average uh, vertical stress at these two are different, so we can take it as differently. And okay, so let us see. So our equation was QUS is equal to sigma average K tan delta AS, right? So let us divide it into two layer 1, which is above water table. So for that, QS will be equal to, QS1 will be equal to, what is average? 0 plus 86.4 by 2. This is our Q average, sigma average, into K. K is equal to 1. Tan delta, delta we found out as 22.5. So tan 22.5. Okay. So this turns out to be 17.81 kPa. Similarly for layer 2, QS2 will be average. It starts from 86.4 plus, at the base it is 180.5 divided by 2 into K is 1, tan delta is 22.5. This will be uh, 55.28 kPa. So I can write this thing. So QS, I can write it as QS1 into AS1 plus QS2 into AS2, right? The first layer and the second layer. First layer is 17.81 into AS1. AS1 is nothing but the perimeter into length, right? So perimeter is 4 into zero point 0.4. What is the length? Length is 5 meter for layer 1. So that is 5 plus 55.28 into, that was QS1, perimeter again zero point 0.4 into 4 into length, what is 10.24, right? 10.24. This turns out to be 1626, sorry, not 1626, 1048.8 kilometer. So our total value is a sum of these two, QUP plus QS, that we will get it as 1262.4 kilometer. So Q safe, again we can get it as Q safe is equal to 1626.5, okay, 4 divided by 2.5. Here we are assuming the factor of safety is 2.5 and 650.56 kilometer. Again, if you, since I'm writing this because I'm going to subtract the self weight again as we had done before, but this self weight will become more insignificant when we have a better capacity, greater capacity. That is here in this case our phi value was very less, 30 degree. That's why our NQ value is also very less. That's why we are finding a very letter, very small value. So it is getting considerable. That's why I'll add QU. Okay, so I'll subtract this W again. The weight of the thing is same as before. So we can write QU, Q safe. We can subtract it as 1626.4 minus 58.52 divided by 2.5. This will be 627.15. Okay, kilometer. So if you just, it will slightly reduce. So this is actually not needed in many cases when the loads that we are dealing with is high. Okay. So I wanted to discuss. Okay, wait a minute. Okay. So I would like to add one more point. That is that here till now, what will happen if we have multiple layer? So let us say we have a layered surface. So we already entered layered actually because we consider the two above water table and below water table as layered. So what if we have layered soil with different phi values and different uh, cohesion or whatever different values? So we can divide. So our, what if our pile is like this? We can find the okay, where did I go? We can take this, we can find out this value, this particular stress, that we can use it for our first term, that is QU is equal to QUS plus, sorry, QUP plus QS. So for QUP, whatever we have in this today's case, we had this thing into AUP, sorry, A base area. So for to find this, we can use this, whatever is at the depth. And for our skin resistance, that is our this thing, this was, okay, this was sigma average into K tan delta into AS, right? So for each layer, that is, first we'll start with this. For each layer, we'll have a sigma, different sigma average, a different sigma K, so different sigma delta, because depending on the phi value. AS also, the area, curved surface area also will be different. So I can write actually this as summation of I is equal to 1 to n, assuming that 1 to n, there are n number of layers, and our average will be also different. I, Ki, tan delta I. You might have seen this somewhere. So this is the idea. So depending on the soil type, this will change. So we can write this in summation form. Okay. The idea is we have to add all these individual layers, capacity resistance are provided by these individual layers, and we have to come up with the this thing. This we'll be discussing more in future. And one more thing is, like, for this last layer, it will be it should also be only to be taken to this. Okay. Another ambiguity here is we are dealing with profile. So till now we only assumed that the the trend of the vertical stress is linear. That is the most simplistic idea, but actually it is not linear in the reality. Depending on the soil, it varies, and it can be something like this. And as we progress, as we go deeper and deeper, this can get linear also. So that's when we come up with a term called critical depth. So what we are doing is, instead of this, we will assume as till a certain depth we have linear variation, and after that we have constant. So whatever we have, so let us say that this is the critical depth. How to find critical depth, we are in the next week, we are dealing with that. So this will be gamma LC, and this will also be gamma LC. So that the point, this is happening because we will come up, will have a longer pipe. So as we go deeper and deeper, it's unfair to take it as linear, which will be a very high value, ending up with a very high resistance, which may not be the case in the field. So having a high resistance means that we will deal with a bigger design load, which is not favorable, which is not ideal, right? So this critical depth we will be discussing in the coming week. So that's all I wanted to discuss apart from this. So um, I hope this session was useful. Uh, you can always post the doubts in the discussion forum. Thank you for joining. The next session will be on 10th, so coming Saturday, by Shivshankar Nandi. And yeah, after that, the coming Monday, 12th, we'll meet again. Thanks for joining again. If you have any doubts, you can always interrupt me in between the session. Also, write the comments. Also, you can post the doubts in discussion forum. Thank you, everyone, and have a nice day.